Light never pauses. In the vacuum between stars, in the space that seems empty but is not truly empty at all, a photon is always in motion. If you could ride alongside a single particle of light, you would find that it refuses to slow down by even the smallest amount. It travels at a constant speed that we call the speed of light in a vacuum. We can give it a symbol such as c. But the deeper truth is that this speed is built into the architecture of reality itself. It is not a choice made by light. It is a rule imposed by the structure of space-time. Imagine a flashlight switched on during the darkest night between planets. The beam does not ask permission to move. It spreads outward instantly, covering distance faster than anything else ever could. Even gravity cannot send a signal faster. Light is the universe storyteller. Every star, every galaxy, every flicker of radiation from the beginning of time is carried to us on photons that never rest. Yet this perfect speed has a strange twist. If light were to somehow look at the universe from its own point of view, everything would appear flattened. Time would no longer pass. There would be no before and no after. The entire journey would seem to take no time at all, because at this ultimate pace, the usual rules that govern motion no longer apply in the familiar way. Photons do not experience time the way matter does. They are both here and there instantly, at least from their own impossible perspective. So if light never slows, how can gravity affect it? How does a beam from a distant star bend when it travels past a massive object like a planet or a black hole? For a very long period, scientists thought that gravity pulled on objects by some invisible force, and they imagined that light would be unaffected since it has no mass. But this view was incomplete. Albert Einstein revealed that gravity is not a force pulling downward on objects, but instead a curvature of the stage upon which everything travels. Space and time form a single connected structure called space-time, and mass or energy tells space-time how to curve. Light simply follows the shape that space-time provides. A photon never changes its speed. Instead, the road beneath it bends. Picture a marble rolling across a trampoline. If someone places a heavy ball at the center of the trampoline, the surface curves. The marble does not slow down, but its path is redirected. It rolls toward the dip created by the heavier object. Light behaves in this same way. It is always trying to go straight, but straight paths are not always what we imagine. Straight is defined by geometry, and gravity controls the geometry. When a photon passes near a star like our Sun, the space-time around that star is curved. The photon continues on what it believes is the straightest possible line, but the line itself is bent. Astronomers have actually observed this effect. During a total solar eclipse in the year 1914, starlight passing near the Sun was seen to shift its position slightly in the sky. It was the first solid confirmation that gravity bends the path of light, not by pulling on it, but by altering the meaning of straight. This bending can produce spectacular effects across the universe. Light from faraway galaxies can travel around closer galaxies, creating rings or multiple images of the same object. These cosmic illusions are called gravitational lenses. Sometimes we see a galaxy duplicated or stretched into arcs of shimmering color, all because gravity has sculpted the path that photons are allowed to take. So light can be curved, it can be redirected, but can it be trapped? Can gravity create a situation so intense that even the fastest traveler in existence becomes caged? Here we find a more subtle truth. Light does not slow down. It never stops, and it never chooses to turn around. But if space-time itself is arranged in just the right way, then a photon can be forced into a looping path. It can run endlessly without escape, not because something grabs it, but because the geometry leaves no open route outward. This idea challenges our intuition. We think of speed as the key to freedom. If you are fast enough, you can outrun anything. Light is infinitely fast compared to everything else, so should it not be infinitely free? Yet gravity rewrites that logic. Freedom depends not only on speed, but on the landscape. If the ground curves back toward the center, if every possible direction leads eventually inward, then even the fastest traveler becomes a prisoner of the terrain. This is what it means to trap light without slowing it. The photon is still racing along at its eternal pace, but every step it takes only leads it back to where it began. The cage is invisible, built not of walls, but of warped geometry. The path of light is called a geodesic. It is the closest thing the universe allows to a perfect straight line. When gravity grows stronger, these geodesics twist and can even wrap upon themselves. The photon is not captured by an external grasp. It is simply obeying the only route that space-time permits. The jailer is the shape of the cosmos, and here lies a profound shift in understanding. When we speak of trapping light, we do not mean that its speed is reduced. We mean that escape becomes geometrically impossible. Light is a runner who never tires, yet the track beneath its feet can curve into a loop. It will never stop running, but it will never reach the finish line either. This is the beginning of our exploration. Light is relentless and unstoppable, yet the universe contains landscapes capable of confining even the unstoppable. As we move forward, the question evolves from how fast light travels to how space itself controls its destiny. The key lies not in speed, but in the structure of the cosmic map. Light's journey across the universe is guided by invisible rules. When we say that photons follow space-time, we mean that they surrender control completely. They do not steer. They do not decide. They simply exist in motion, and the motion is dictated entirely by geometry. The fastest thing in existence behaves like a leaf carried on a river. The river is space-time, and its currents are gravitational curvature. But there is something even more remarkable hidden in this idea. Light has no mass, yet it is still bound to the shape of space-time. That means gravity does not need to pull on matter in order to influence motion. It can direct even the movement of the massless. This is why Einstein's revelation was so disruptive. It said that the universe is not filled with forces acting at a distance. It is instead a flexible stage, constantly molded by everything that exists on it. When a photon leaves its birthplace inside a star, it is not simply flying outward through emptiness. It is weaving through a constantly shifting architecture. Every planet, every star, every swirling black hole pushes and stretches the geometry. Even the light from the star itself contributes to the curvature, though only slightly. Photons are both travelers and builders in the cosmic landscape. Now imagine that landscape becoming extreme. Imagine a place where space-time is bent so tightly inward that all routes available to light begin looping back. A photon sent outward finds itself circling, not because it slows or hesitates, but because a way no longer exists in a meaningful direction. This happens near the most compact objects in the cosmos. Black holes are the strongest example, where light can orbit at a special distance we call the photon sphere. But even objects that fall short of becoming black holes can nudge space-time toward this strange configuration. Before we examine those exotic scenarios, we must finally confront a subtle point. When scientists say that light follows the shortest path, they are using a word that behaves differently in curved space. The shortest path may be a circle if the geometry twists in the right manner. The word straight does not mean what our intuition thinks it means. Straight is defined by the nature of the environment, not by the traveler. A photon near a dense star believes it is going straight. It does not realize that its path is bending, because bending and straight are illusions created by context. This is why light passing by a massive object appears curved to us. We sit at a distance and judge the path relative to flat space. The photon only knows the shape of the road it must follow. If space-time becomes curved enough, the photon's road can fold inward again and again. The path refuses to let the photon escape. Its freedom is lost, not through restraint, but through crowding the geometry into a trap that never allows outward direction to grow bigger than inward direction. There is a critical balance where escape becomes nearly impossible. In such places, time itself begins to behave strangely. When gravity grows stronger, time slows compared to regions with weaker gravity. This is a real effect, measured with clocks near Earth's surface and on orbiting satellites. The deeper you go into a gravitational well, the slower your clock ticks relative to distant observers. Now imagine a photon near a surface where gravity is so strong that time nearly freezes. The photon is still racing at the speed of light locally. It feels no change in its speed or in the rate events unfold. But someone watching from afar sees the photon creeping, almost stuck in place. To that distant observer, the photon looks imprisoned by time itself. Even without becoming part of a black hole, the environment can delay the photon so severely that the outside universe effectively loses track of its motion. It is like a movie slowed down until each frame lingers for centuries. We might reasonably ask whether that counts as trapping. The photon still moves. It will eventually escape if the object does not collapse further. But from our perspective, it behaves as if caught. The very concept of escape becomes slippery here. What does it mean for light to escape? Does escape require reaching open cosmic territory within a human lifetime? Within a billion years? If the delay becomes longer than the age of the universe, is that different from permanent imprisonment? These questions are more than philosophical. They help define the boundary between possible and impossible. Gravity can create almost perfect cages that hold light for unimaginable periods. Yet if we are strict, only black holes achieve total confinement. Everything else falls short by a hair. Space-time must be warped into an extreme that cuts off all paths outward. Otherwise, given enough time, motion returns to the cosmos. So we return to the central paradox. Light is always free in speed, but not always free in direction. Curvature can steal the routes that would lead to escape. The photon remains unstoppable, but trapped in a loop that repeating endlessly. Light does not lose energy or slow down. It simply never gets anywhere new. Each photon is like a thought racing through the mind of the universe. It is a sign that geometry has something to say. Every path it follows reveals the structure of reality. And when light becomes trapped, the story it tells becomes haunting. The fastest traveler in nature finds itself imprisoned not by chains, but by the very fabric of existence. Light is a messenger that never forgets its mission. Even when gravity tries to twist its course into impossible shapes, a photon remains endlessly determined. It does not think, it does not choose, yet its behavior reveals the deepest structure of reality. When light refuses to escape a region of space, we learn something profound about the nature of gravity itself. Consider the difference between an open plain and a deep valley. If you release a marble in the plain, it can roll away forever. If you release it in the valley, it might roll up a slope for a time, but gravity will always pull it back down. A photon experiences a similar fate when space-time curves inward. There are places in the universe where even though space is technically open, the curvature imposes a hidden valley that light cannot overcome. It tries to surge outward, but spirals back, drawn not by a pull, but by the absence of any straighter path. These effects occur around the most compact objects known to exist. Imagine a star so dense that a single teaspoon of its matter would outweigh mountains. That star bends geometry so severely that light passing near it may complete many loops before finally breaking free. Our telescopes sometimes detect several images of the same cosmic object caused by this precise effect, repeated arcs from photons that took slightly different winding routes around a massive body. Sometimes the looping path becomes so tight that it almost forms a closed circle. A photon might go round and round for centuries, brushing endlessly against the boundary between freedom and surrender. Yet the orbit is never perfectly stable. The slightest disturbance pushes the photon either inward toward disaster or outward toward escape. This delicate balance shows how close nature can approach the miracle of trapping light without truly achieving it. The universe loves thresholds. It pushes conditions toward the edge of transformation. A massive star, just shy of collapsing into a black hole, still shapes space fiercely. Its surface becomes a region where light struggles to climb away. Observers far from the star would see its photons stretched into longer and longer wavelengths, losing energy to the gravitational well. The light would appear dimmer, redder, and slower to escape. At some extreme point, the delay becomes practically infinite. Even though the photon is moving at full speed in its own local rhythm, we witness a motion stretched across eons. There is something chilling about the idea that a photon can be imprisoned without knowing it. From its perspective, nothing unusual is happening. It is still racing through the universe. Time, to a photon, has no length. The journey is immediate, yet to someone watching from safety, the photon appears caught forever in the grip of gravity. It shows how time and perspective are not universal truths. They are fragile agreements shaped by where you stand. This leads us to the heart of the mystery. When does confinement become real? Does the universe recognize imprisonment only when a black hole forms, sealing light behind an event horizon from which no signal can ever return? Or does the illusion of trapping count, if from every possible external viewpoint the photon is lost to the cosmos for longer than the universe itself will exist? The science suggests a strict answer. True trapping means a complete absence of escape routes. The moment any direction remains open, even if the path demands a journey lasting longer than stars remain lit, the photon is not truly caged. It is delayed. It is hindered. It is misled by geometry. But it is not defeated. This distinction is vital. It tells us where the line is drawn between matter that merely bends space and matter that breaks it. It shows that light remains a perfect symbol of cosmic freedom, restrained only when space-time becomes so intensely curved that freedom itself ceases to have meaning. A black hole is not just a place where light cannot leave. It is a place where the very definition of leaving becomes impossible. Every step forward in understanding reveals more layers of wonder. Gravity does not need mass to do its work. It sculpts the paths of even the massless. It takes the universe's fastest traveler and toys with it, slowing its appearance to a crawl, forcing it into spirals and loops, nearly snaring it forever. Yet the photon never stops. It never concedes. It never experiences the prison that we observe. So we end this chapter with a new appreciation for the strange balance between speed and geometry. Light moves as fast as physics allows, yet it remains at the mercy of the landscape carved into space-time by gravity. Freedom is not guaranteed by velocity alone. It depends on directions that remain meaningful. When gravity strips those directions away, the unstoppable can be stopped without ever slowing. We now stand ready to investigate the places in the cosmos where this balance is pushed to the very edge, where stars nearly trap light, where photons orbit in precarious rings, where space becomes a maze without walls, and time becomes a barrier without doors. The journey of light is not just swift, it is fragile. Gravity is not a force that reaches out and grabs things. It is the shape of the universe itself. When we say that gravity attracts, we are describing only the appearance. What is truly happening is deeper. Space-time bends around mass and energy, like a stretched fabric curving beneath a weight. Everything that moves from planets to photons simply follows the curves that already exist. They are not being pulled. They are obeying the geometry. Imagine a traveler walking across a perfectly flat plane. They can take any direction they choose. Now imagine that plane curving inward into a valley. Even if the traveler insists they are walking straight, the path will eventually slide downward, because straight no longer means what the traveler expects. The shape of the world beneath their feet has changed the possibilities for motion. That is gravity. When Einstein revealed this idea, it reshaped our understanding of the cosmos. Gravity is not a mysterious tug, but a silent sculptor. It molds the roads along which light must travel. Even though a photon has no mass, it is not immune. The path it follows is determined entirely by space-time. The photon is like a tiny boat that cannot see the water, but feels every ripple. Planets, stars, gas clouds, dark matter, glowing plasma around galaxies, all of these shape space-time. Some objects barely make a dent. Others produce deep wells that guide the motion of everything nearby. When light from a distant quasar passes near a massive galaxy, its path shifts as if threading through a tight canyon. We observe this as a slight twist in position, or as multiple images of the same object, a visual echo created by curvature. If space-time were perfectly flat, every beam of light would travel forever in a straight line. But the universe is filled with structure. Every piece of mass introduces a ripple in the fabric. Light passing through these ripples encounters new limitations on what straight means. A straight path in curved space can look like an arc or a loop when viewed from afar. The photon still believes it is going directly forward, but forward has been altered by the environment. Gravity does not just steer paths. It changes the very rules of distance and time. Near strong gravitational fields, distances stretch and time slows when witnessed from afar. Light climbs these altered distances the same way a traveler climbs a long mountain ridge. The photon maintains its relentless speed, but the road itself grows harder to traverse. From our perspective, the light appears to struggle against the climb, taking longer to reach us than it would in gentler terrain. We see this around our sun. Signals sent from spacecraft near the sun experience slight delays. These delays were predicted and later measured with precision, not because signals slow down, but because the path through curved space-time is longer than it would have been in a perfectly flat universe. The sun changes geometry, and geometry changes motion. Now imagine something far more massive. A neutron star squeezes more matter into a smaller space than our sun ever could. The curvature near its surface is extreme. Light leaving its surface must travel through a region where outward and inward directions nearly balance. The path outward can twist back, forcing the photon to try again. A beam of light may loop once, twice, many times. It may reveal new sides of its source, showing us regions that should be hidden behind the star. This is gravitational lensing, not just far from an object, but right at its doorstep. The object becomes a hall of mirrors. Photons scatter in ways that allow multiple glimpses of the same event. If you watched a neutron star closely enough, you might see a beam of light circling to reveal a moment repeated like an echo of reality. Gravity decides everything that is possible. Even the direction we call outward is defined by curvature. When the curvature grows strong enough, outward shrinks. The photon is still moving fast enough to cross a galaxy in 1,000,000 years, but there is no longer a free route to travel. The space-time around the photon has turned into a trap made only of geometry. We need to let go of the idea that movement is always defined by speed. Light has perfect speed, but imperfect freedom. A perfectly fast runner cannot escape a maze if the maze twists inward faster than the runner can travel outward. Gravity is the architect of such mazes. Every celestial object contributes to the grand design. When two galaxies collide, their combined mass warps the space between them, like a sheet twisted by giant hands. Streams of dark matter, though invisible, add their own shape. The result is a cosmic landscape filled with ridges, basins and spirals that all dictate the journey of light. Sometimes gravity reshapes paths smoothly, like a gentle curve guiding a stream. Other times it creates sharp bends and narrow tunnels. A photon traveling through the universe experiences all these shifts without hesitation. It is endlessly adaptable. It never slows, never resists, never knows that its journey is being controlled. And yet, beneath this obedience lies the seed of captivity. If the curvature can be intensified, if space-time is pushed to the limits of what physics allows, then the path can twist so tightly that freedom disappears. The photon continues to move, but its future becomes a loop, a tireless run around a prison with no bars. Gravity shapes every destiny. Even the fate of light rests on the balance between the mass that curves space and the geometry that defines motion. The shaper of pathways is also the builder of cages. Gravity does not only bend the roots of light, it shapes our understanding of what motion even means. When we speak of a straight line, we are assuming a calm universe with no distortion. But space is never perfectly calm. Every atom contributes a whisper of curvature. Every star shouts its presence by bending the world around it. The universe is a chorus of influences that together decide how light must move. Think of a river. From above, it may seem to twist randomly through a valley, but the water always follows the lowest available path. Light behaves the same way. It moves along the path that space-time offers as the most direct route. If the riverbed shifts, the water bends with it. If space-time curves, the photon adapts instantly. This obedience creates some of the most beautiful sights known to astronomy. When light from a distant galaxy passes near a massive cluster of matter, the cluster bends the pathways so strongly that circular patterns of light appear. We call these shapes Einstein rings. They are like cosmic signatures of gravity. The faraway galaxy has not changed. Our view has changed. The light that should have missed Earth entirely, instead, wraps around the cluster and converges toward us. Without those massive shapes in the middle, we would never see that galaxy at all. In many ways, gravity allows the universe to reveal its hidden parts. By curving light, it creates windows into regions that lie behind obstacles. It rescues the information that would otherwise vanish into darkness. Yet the same bending that reveals can also conceal. If the curvature grows extreme, light may be sent into a never-ending detour. It is still arriving somewhere, but not where we are waiting to see it. Mass defines gravity. But the size of an object matters as much as its weight. Spread the mass widely, and the curvature is gentle. Compress the mass into a tight ball, and the curvature grows fierce. The surface of Earth bends space-time subtly. The surface of a neutron star twists it violently. The difference between the two is not just scale, but intent. One shapes a path, the other almost traps it. Let us imagine a beam of light emitted near a compact star. The photon attempts to depart the gravitational well. From its local perspective, it moves straight outward, but outward is not as free as it seems. The star is curving space so strongly that the straightest line leads the photon sideways and slightly back. The photon does not notice its captivity until many loops have passed. This is not a force in the conventional sense. There are no strings pulling the photon backward. It is the lack of direction that forces the photon to obey the circular motion. Freedom is a choice of routes. Take away the roots, and freedom fades. A strange thing happens when light is forced onto near circular paths. Small disturbances become very important. A gentle push may send the photon spiraling outward again. A tiny nudge in the opposite direction may send it inward toward the star surface, and perhaps into destruction. We call these paths unstable. They demand perfect balance to endure. The photon peaks into the possibility of being trapped, but that future is never guaranteed. Where does that leave the idea of a perfectly stable orbit for light? Is there truly a way to build a prison that holds a photon without any hope of release? Nature answers cautiously. In some of the boldest theoretical ideas in modern physics, objects like boson stars or gravastars may possess deep wells of curvature that could hold photons for meaningful lengths of time. These ideas are not proven. We cannot yet confirm they exist. But if they do, they might represent a halfway step toward the total confinement seen in black holes. In our own universe, space-time responds not only to mass, but to energy as well. Light itself has energy. Gravity can therefore bend light, and light in large quantities can contribute to gravity. The result is a feedback loop in extreme situations. Radiation near a collapsing star may delay its own escape by deepening the curvature that is slowing it down. The star becomes a struggle between outward pressure and inward bending. If the curvature wins, the star shrinks further. Eventually, the battle might produce a black hole. But before that final outcome, the star can create conditions where photons remain trapped for long periods, even without vanishing behind any horizon. This brings us to a crucial realization. Light is not trapped by force. It is trapped by circumstance. Its speed gives it power, but the environment can negate power by removing options. A photon always rushes ahead, but if a head folds back inward, Speed no longer means escape. We also must confront the role of time, near intense. Gravity, time slows down. A photon orbiting a compact object might complete a full loop in what feels like an instant to that photon. But for a distant observer, each loop might take ages. If the time dilation becomes enormous, the photon appears to hang forever on the edge of escape. It is racing around the object again and again in its own timeless reality. And yet to us, it is frozen in place, trapped not by walls but by the strange shifting of moments themselves. There is a haunting beauty in this. Light reveals the shape of reality by following its rules. When those rules become distorted enough, the story light tells becomes trapped inside the tale itself. The photon continues to move, but its message never reaches new ears. The more we learn about gravity, the less it resembles a simple pull downward. It is instead a redesign of possible futures. It permits only certain trajectories. It erases others. Even time is redesigned in its presence. A universe with gravity is a universe where motion is deeply conditional. This chapter is about that condition. It is about the difference between motion through free, flat space-time and motion through a world where mass has curled the playing field. It is about how a photon can stay loyal to its speed, yet lose its freedom to escape. Gravity is a subtle tyrant. It never touches the photon, yet the photon cannot disobey. Gravity is a quiet author. It writes the script for every journey in the cosmos. When a beam of light begins its path, gravity decides which futures are allowed. It places invisible boundaries beneath every photon, and those boundaries can shift depending on the company light keeps. The presence of extreme mass can twist space-time so inwardly that every direction a photon takes begins to bend back toward the source. Yet in this twisted region, the photon is never ordered to halt. Its speed is untouched. Its energy is unchanged, unless climbing outward. But its fate is altered. The road beneath it curves, and the geometry may lead it to circle again and again with no obvious escape. This tells us something profound. The freedom of light is not defined by its speed. It is defined by geometry. Speed alone cannot save a traveler if the road loops infinitely. Gravity can construct these loops. Sometimes they are gentle spirals that eventually widen enough to allow escape. Sometimes they are tight coils that take ages to unwind. And in the most extreme environments, they become infinite circles from which there is no release. Einstein's equations describe exactly how this happens. When matter compresses enough, it reshapes the metric, which is the mathematical description of distances in space and intervals in time. Around a normal star, the metric is only slightly deformed. Light curves a little, escapes easily. Around a neutron star, the metric is strongly warped. Light curves sharply, may struggle to rise outward, and near a black hole, the metric collapses inward fully, leaving no path that leads outward once the boundary known as the event horizon is crossed. The rules change gradually as mass and density increase. There is no single threshold where light suddenly becomes trapped. The experience transitions from total freedom to limited freedom to impossible escape. This gradual shift reveals the true identity of gravity as a master of direction. It does not slow the photon. It removes the direction that would lead to safety. Imagine standing near a whirlpool. The water flows inward. You can paddle outward as fiercely as you like, but as you get closer to the center, every outward stroke feels weaker. Eventually, no matter what direction you face, the flow pulls you inward. Not by force, but by the geometry of motion. The swirling shape of the water governs the possibilities. That is what gravity does to space. Now take that whirlpool and remove the water. Remove the force. Remove the particles. Leave only the shape. What remains is the invisible curvature of space-time. Light swims inside that curvature. It is the perfect swimmer, the fastest traveler in existence. But the current can still redirect it endlessly. This understanding helps us see why the cosmos looks the way it does. When we observe distant galaxies, we see arcs of light that were never meant to reach us. Gravity has brought them to us, folding their roots inward, like threads woven into a grand tapestry. These patterns tell the history of every object light has passed. A beam does not simply travel. It remembers the curvature of every region it crossed. The image we observe contains these memories disguised as distortions. Sometimes gravitational curvature reveals secrets. It lets us map dark matter structures that do not shine. It allows us to see galaxies hidden behind others. It brings the distant closer and the invisible into view. Yet that same effect can also erase meaning. If curvature becomes too strong, photons never escape. They never tell their story to anyone outside their prison of warped space. So when we ask whether light can be trapped without forming a black hole, we are really asking how far gravity can push geometry before it collapses the idea of escape. The answer is that space-time allows many stages of confinement. There are places where light can circle for ages. There are pathways so twisted that most photons never find a way out. There are stars that nearly achieve the same grip on light that black holes do, yet they never quite succeed. There is always one direction left, one subtle path that allows release, even if that release requires a journey older than galaxies. But this almost trapping of light reveals how close reality can approach the boundary of the impossible. A compact star with extreme curvature becomes a preview of the black hole, a rehearsal of the final act. If the star shrinks a little more, its grip on light closes fully. Direction ceases to include escape. A horizon forms. Light no longer even attempts to flee. Gravity is patient. When a massive star burns through its final fuel, radiation pressure drops. The star can no longer resist the inward push of gravity. The curvature deepens. Time slows near the surface. Photons climb outward with such struggle that their wavelengths stretch into invisibility. The star darkens. The geometry tightens further. And eventually, a point of no return emerges, where space curves so steeply that a photon always finds its next moment deeper inside. That is the birth of a black hole and the death of escape. But before that death, there is a long twilight, a stage where the star almost encloses light, where the freedom of photons is very nearly revoked. In this stage, light lives a life of uncertainty. It rushes forward with all its speed, but finds its steps leading nowhere new. It loops and waits. It struggles against a shape stronger than its desire to flee. Gravity is the shaper of pathways. It is also the designer of boundaries. Every photon follows its guidance, willingly or not. When the pathways shrink, when the boundaries grow tall, light can lose its freedom while still racing forward. The photon becomes a prisoner of space-time, a runner with no finish line. This is the truth we have uncovered. Gravity decides the fate of motion. It determines whether a path leads outward to the stars or inward to the abyss. Light reveals this truth perfectly, because light never stops. When even the unstoppable becomes trapped, we learn that freedom itself is a product of geometry. The next chapter will bring us to the very edge of the ultimate trap, a place where light does more than bend, where it orbits in a balance so fragile that a single trembling atom could break the loop, a place that lies just outside the final darkness. There exists a boundary in the universe where light hesitates. It is not yet lost, but it is no longer free. This boundary surrounds every black hole, forming a delicate ring where photons can orbit forever if they could achieve perfect balance. Scientists call this region the photon sphere. It is a place where the geometry of space-time becomes curved so tightly inward that the straightest path for light is a circle. Imagine a photon released at just the right distance from a black hole. It races forward as it always does, but forward has been twisted into a loop. The photon might circle the black hole many times, endlessly repeating its path. But this orbit is not safe. It is not stable. The slightest push, even the smallest influence from another passing particle or a faint ripple of gravity, will knock the photon off its track. One tiny disturbance, will send it spiraling outward into the universe, or tumbling inward into the darkness that consumes everything. This fragile place lies just outside the event horizon, the ultimate one-way boundary. The event horizon is the line that light cannot cross and still escape to tell its story. The photon sphere, however, sits farther out where escape is still theoretically possible, though difficult. It is the last battleground for freedom, a thin layer where the universe allows one final chance for survival. The existence of a photon sphere reveals something crucial about the nature of black holes. The object does not have to pull on light. It simply removes all other paths except the one that loops around it. The photon obeys this geometry. From its own perspective, it is still going straight. Yet the road beneath it is coiled into a circle by the intense curvature around the black hole. There is a special distance where this circle forms. Scientists describe it using the Schwarzschild radius, the measure of the event horizon for a non-rotating black hole. The photon sphere exists at 1.5 times that radius. If the black hole were as large as a city, this orbit would sit just outside its invisible surface. If the black hole were as massive as a star, the sphere would be a ring of light hovering near its edge, unseen, yet powerful. Although we cannot see photons that are perfectly trapped, we observe their influence. When a black hole is surrounded by glowing gas, photons that skim around the photon sphere create a bright, thin ring in the image. The first picture ever captured of a black hole revealed exactly this. Humanity saw a halo of light encircling the shadow, the signature of photons that nearly found themselves imprisoned by geometry. These circling photons live on a knife edge between existence and erasure. If the black hole grows more massive or spins rapidly, the photon sphere shifts and warps. Rotation twists space-time like a whirlpool, pulling the paths of light into spirals that lean one way more than the other. Some photons may find a slightly easier escape route, while others are spun inward faster. The direction of motion becomes part of the equation. The future of the photon becomes a matter of luck and symmetry. Even though the photon sphere is outside the black hole, time behaves strangely here. To a distant observer, the circling photon seems to orbit more slowly than it actually does, because time is stretched by the gravitational well. Each loop becomes a lingering moment as the photon battles the curvature. To the photon itself, there is no hesitation. There is only forward motion at the ultimate speed. The differences in perspective reveal that freedom itself is not absolute. It depends on where you stand. In this place so close to oblivion, the world behaves differently. Directions that normally exist become distorted. Upward and outward lose meaning. For the photon, the only future aligned with its path is one that curls back on itself. The universe here is a closed track with no exit. The photon is like a race car driven around a circular track forever, not by choice, but by the shape of the road. Astronomers call this kind of path a null geodesic. It is a straight line according to the rules of space-time near a black hole, but to observers watching from afar, it appears as an orbit. The photon follows the rule of minimal distance through a terrain that refuses to allow any shortcut to freedom. The photon sphere is also responsible for some of the strangest illusions in astrophysics. Light that loops around the black hole multiple times before escaping can produce several images of the same star or galaxy. These images appear stacked like ghostly echoes, decreasing in brightness with each loop. We rarely observe these directly because the light loses energy each time it fights its way outward. But the mathematics confirms that such echoes are real. All of this shows that the photon sphere is more than a boundary. It is the ultimate demonstration of how gravity sculpts destiny. At this distance, escape is still possible. The photon may eventually slip free and race into space once more, carrying the story of its impossible journey. Or it may fall inward forever, crossing the horizon and vanishing from the visible universe. Each photon near the sphere lives with this uncertainty, a fate decided by the lightest nudge. This delicate dance reminds us that the universe does not operate with sharp divides. Instead, it offers regions of gradual transition. The photon sphere is one such region, where light nearly loses its independence but not quite, where possibility remains, even if just barely, where the difference between liberty and imprisonment is the thickness of a thought. Here, the laws of motion lose their simplicity. The fastest journeys become circles. The straightest paths turn inward. The meaning of escape begins to dissolve. Light finds itself chained to curvature so perfectly that it cannot tell whether it is moving forward or forever returning to where it began. The photon sphere shows us the border between almost trapped and truly lost. It shows us that light does not need to slow down to become confined. It only needs a universe where every direction curves toward the unknown. Light that ventures near this critical distance behaves as if it is walking along the edge of destiny. The photon sphere does not simply curve its path, it redefines what it means to move forward. A photon circling here travels around the black hole in an endless attempt to reach somewhere new. But somewhere new has vanished from its horizon of possibilities. Forward is a loop, not a direction that leads outward. The idea that a straight line can become a circle sounds impossible until we remember that straight is not an idea defined by humans. It is defined by geometry. When geometry bends hard enough, the shortest route between 2 points can bend into a closed shape. A photon moving through such a landscape continues to follow the rule of straightness. It simply does not realize that straightness now means circling the abyss. If gravity grew slightly weaker, the photon would escape after a single wide loop. If gravity grew slightly stronger, the photon would spiral inward and lose itself behind the event horizon. But at the photon sphere, the photon is caught in a perfect compromise. Every attempt to lean outward is matched by the curvature pushing inward. Every attempt to approach the surface of the black hole is balanced by that same curvature, forcing the photon to drift outward again. It is not balance in the peaceful sense. It is balance like a pencil standing on its tip, poised to fall at the slightest flutter. Observers far away from the black hole would not see the photon dancing at full speed. They would perceive the motion slowed and stretched by gravitational time dilation. The photon keeps racing, but the ticking of time near the sphere is so altered that the movement appears reluctant, almost hesitant. The signals sent by the photon must climb out of the gravitational well, losing energy along the way, shifting into redder and redder wavelengths until they nearly disappear into darkness. The photon sphere is not a surface that can be touched. It has no solidity. It is not made of matter or energy. It is made purely of geometry. If a game of marbles were played across the fabric of space-time, this would be the circle drawn not by chalk, but by the curvature of reality. A photon following that circle is obeying the deepest laws of physics. There is no trick. There is only shape. And yet this shape sits just outside the ultimate trap. The event horizon is the place where escape is not merely difficult, but impossible. Once light crosses that boundary, it can never climb outward to tell any story again. The photon sphere is an outer border of influence. It is the realm where gravity has become strong enough to force light into looping orbits, but not quite strong enough to eliminate the possibility of freedom. Most photons that enter this region will pass through it eventually, but a few can become snared in precarious cycles, slipping around the edge of eternity like dancers moving on a wire stretched above an endless void. When astronomers study black holes, they do not see the horizon itself. It is invisible by definition. What they see is the glowing matter swirling around the black hole and the thin, bright ring produced by the photon sphere. This ring gives the black hole its silhouette, like a halo of trapped intentions. The shadow within that ring is the footprint of a region where even light cannot survive escape. The photon sphere is a promise and a threat. It promises that photons still have a chance to leave. It threatens that the slightest mistake will send them into a place from which there is no return. The photon does not know this danger. It does not know anything at all. It just follows space-time. But we, from our distant vantage, watch this balancing act and understand the stakes. There is beauty in how nature approaches extremes. It never leaps straight from freedom to confinement. It builds regions of suspense, regions where rules nearly break, but manage to hold. The photon sphere is one of these regions. It is a stage where the laws of motion seem to hesitate before surrendering to a deeper power. Every photon that reaches the sphere arrives with a past filled with travel across calm and gentle regions of space. It has crossed interstellar distances guided by almost flat geometry. Then suddenly, the rules shift. The future becomes uncertain. Its destiny may be to escape and continue shining outward to observers like us, or it may be to cross the last threshold into darkness, carrying its message forever into silence. Physicists study this region to understand not only black holes, but the very nature of gravity itself. The photon sphere reveals how far the universe can push curvature while still allowing motion. It shows where the boundary lies between directed trajectories and those that lead nowhere new. If you imagine the universe as a vast network of pathways, the photon sphere is where those pathways break apart. Some lead out to far galaxies, some fold inward into the black hole, and some loop forever, refusing to pick a side. Here, light lives on the edge of all possible futures. The photon sphere teaches a lesson about the fragility of freedom. It is not enough to move quickly. It is not enough to be unstoppable. If the world itself curves in the wrong way, even the unstoppable can be redirected into a circle without end. It reminds us that control does not always require force. Sometimes it only requires removing all other options. What makes this even more extraordinary is that the photon continues its run as if nothing unusual is happening. It still moves at the universal speed. It still follows what it believes to be a straight path. It does not sense captivity. Its prison is invisible and defined only through perspective. To the photon, there is no prison. To the observer, the photon is nearly lost. This is the tension that defines the photon sphere. The boundary where reality changes shape and light must negotiate with geometry. The place that divides hope from inevitability. The final moment where the universe allows the possibility of escape. Light that dares to approach this boundary performs the strangest dance known to physics. A photon near the photon sphere is a traveler walking a razor's edge between infinite survival and instant doom. There is no middle ground. If the photon tilts ever so slightly outward, it will escape and continue on through the cosmos for untold ages. If it leans even the tiniest amount inward, it will plunge into a fate from which not even time can rescue it. It is the purest example of how gravity shapes choice. A photon at this distance is granted exactly two futures, and the difference between them is so subtle that nature itself seems uncertain which will occur. To imagine this danger, consider balancing a marble on the peak of a perfectly smooth hilltop. The marble never stays still for long. A breeze, a tremor in the ground, even the shifting of air molecules is enough to tip it over. The photon sphere is that hilltop, except the marble never stops rolling. It shoots around the peak at light speed, trying intensely to follow a straight route. But the geometry underneath it curves so harshly that straight is a circle, and every circle it completes only increases the chance that some disturbance will push it into one direction or another. In a universe filled with motion and chaos, disturbances are inevitable. Waves of gravity ripple through space-time whenever massive objects collide. Particles of radiation are constantly born in hot and violent regions near black holes. Even the swirling gas and dust around the event horizon create subtle pushes and pulls. A photon locked into orbit at the photon sphere is like a feather caught in a storm. It may cling to its path for a short while, but sooner or later, the storm will win. When we look at images of black holes taken by massive telescope networks spread across Earth, the glowing ring we witness is made in large part by light that has skimmed this boundary. Photons that circle the black hole 1 or 2 or even 3 times before flying outward carry with them the imprint of that incredible curvature. They show us the silhouette of the event horizon not by touching it, but by risking their freedom in its gravitational grip. If a photon could somehow maintain a perfect circular orbit, it would never age. Time for a photon is always frozen, because photons do not experience time. Their existence is a never-ending now. But to an observer watching from far away, the circling photon's story would unfold with eerie slowness. Minutes might stretch into hours, hours into centuries, and centuries into forever. The image of that photon would fade, shift, and eventually blend into darkness as its energy drains away in its attempt to escape the gravity well. The strangeness of this region tells us something profound about the nature of perception. Freedom is not the same for all observers. To the photon, nothing has changed. It is moving normally, obeying the only law it has ever known. To us, it is as good as captured. To an observer falling inward alongside the photon, the motion might seem fast and decisive. But to us, watching from safety, it becomes a ghostly figure haunting the edge of a void. The photon sphere also influences the behavior of matter. Gas spiraling into a black hole will heat up and glow more intensely as it approaches this region. Because light struggles so much to escape, energy builds and bursts outward in the form of radiation that we can detect across galaxies. The fiercest fireworks in the universe occur at the edges of this invisible ring, the last cries of matter before it disappears forever. One day, the photon may finally escape. Its long imprisonment ends with a single lucky deviation in its path. It races away from the black hole and eventually finds a home in the eye of a telescope or on the surface of a distant planet. After so many loops around the abyss, it brings with it a story that took ages to complete. That single particle of light becomes evidence that even near the strongest trap nature can create, freedom can persist. It may take time beyond human understanding, but it is not impossible. This fragile balance reveals the difference between almost trapped and truly trapped. At the photon sphere, every future still contains a tiny crack of possibility. Light can continue its role as messenger, but cross a little deeper inward and the crack seals permanently. The photon sphere is the last region where hope exists. Everything about this boundary is unstable, precarious, temporary. It is the universe whispering that perfection is impossible. Even the conditions needed to trap a photon at this distance are too exact to last. And so the photon sphere remains a place of tension, where nature stretches itself toward the edge of absolute confinement, but never quite reaches that point. What lies just beyond this boundary is not simply darkness, it is the end of storytelling. No photon that enters the event horizon escapes to tell any tale. The photon sphere is the final ring of light before silence. It is the last visible moment where the unstoppable traveler still has a chance to rejoin the universe it came from. Now that we have witnessed this precarious orbit, we must ask a daring question. If black holes are unmatched in their ability to trap light so tightly, are they truly unique? Or are there other objects, just shy of becoming black holes, that can twist space-time nearly as strongly? Can stars that have not collapsed all the way imprison light for long periods without crossing that final barrier? To answer that, we must look to some of the densest objects still visible in the universe. Stars that have shrunk and hardened under their own gravity, but have not yet become pure darkness. Stars that challenge the photon sphere's monopoly on trapping light. A neutron star is what remains when a giant star dies, but refuses to vanish entirely. The original star may have been many times more massive than our Sun. For millions of years, it fused hydrogen into helium, helium into heavier elements, releasing light and heat that pushed outward against gravity. But every star carries within it a countdown. When the fuel runs out, gravity takes control. The core collapses inward with unimaginable violence. Electrons are crushed into protons, forming neutrons packed tightly together. The result is a star so dense that a spoonful of its matter would outweigh mountains. The entire city-sized sphere contains more mass than our Sun. In such a place, space-time twists sharply. The curvature pulls inward with nearly the same intensity that we see at the edges of black holes. Here, light is not only bent, it is nearly captured. A photon, leaving the surface of a neutron star, must climb a gravitational cliff. Each step outward is a victory against a geometry that wants to drag it back. From far away, light from a neutron star looks tired. It struggles upward through warped space-time, and as it climbs, it loses energy. Its color shifts toward red. The star glows, but the glow is dimmed and stretched by the grip of gravity. The very act of escaping costs the photon part of its identity. It still travels at the absolute speed. Yet to an external observer, the journey takes longer and looks weaker than expected. Neutron stars push gravity to the brink. They do not form photon spheres like black holes do, but they nearly achieve something similar. Photons passing close to the surface can complete partial orbits. They loop once, sometimes twice, before breaking free into space. If you could stand on the surface, which is impossible, you might see the back of your own head. Light leaving your body could arc around the star and return to you from behind, giving you a full view of yourself without turning around. The star becomes a lens that reveals every side of everything. Astronomers who study neutron stars see evidence of this bending. Some neutron stars emit beams of radiation from their magnetic poles. As the star spins, the beams sweep across the sky like lighthouse signals. We call such stars pulsars. The flickering we detect is shaped not only by the rotation, but by the extreme gravitational curvature surrounding the star. Some pulses arrive distorted or delayed because the photons had to follow looping paths to reach us. The surface of a neutron star is not smooth or silent. It may crack under stress, releasing tremors that send vibrations through the dense crust. These quakes shake magnetic fields powerful enough to distort space-time further. A photon caught in the chaos of such a moment must navigate sudden shifts in its pathway. Some photons are pushed slightly closer to the star and spiral inward. Others are nudged outward and finally earn their escape. If a neutron star gains too much mass, perhaps by stealing matter from a nearby companion star, it may cross a critical threshold. The pressure of neutrons resisting further collapse will no longer suffice. Gravity will tighten its grip. The star will continue shrinking. The curvature will deepen until the escape routes for light vanish completely. At that moment, the star becomes a black hole. The transformation is silent. No flash marks the dividing line. Light simply stops returning from the surface. The photon sphere forms, and the last glimpses of the star fade into the darkness. But before that final collapse, neutron stars occupy the narrow zone between visibility and oblivion. They are cosmic tightropes between what can be seen and what can be trapped. Their gravitational pull is strong enough to delay light for ages. A photon near the surface may wander in long arcs before reaching space. Some that begin their journey outward may hesitate so long that by the time they finally escape, the star that emitted them has transformed entirely. This creates a strange possibility. There could be photons traveling right now that were born in the light of a neutron star long before humans existed. They have been circling and climbing slowly through twisted space-time for ages. Only now do they break free and continue outward toward distant observers. They bring with them stories from a universe older than our civilizations can imagine. Neutron stars show that the boundary between a free photon and a trapped photon is not clean. It is a gradient that depends on density, structure, and time. The photon remains fast. It remains energetic. Yet the universe can delay its freedom until the meaning of freedom becomes uncertain. The geometry around these stars teaches us that trapping does not require a sealed prison. It only requires a struggle that lasts longer than the moments we are able to witness. Light is not forbidden from escape. It is simply challenged so severely that escape becomes unlikely, delayed, or nearly forgotten. This existence on the threshold reveals just how powerful gravity can be without fully silencing the universe message carrier. And so, neutron stars stand as monuments to near imprisonment. They prove that light does not need a black hole to lose its way. Space-time needs only to curve strongly enough that the path outward becomes too narrow and too long to traverse easily. A photon might still break free, but only after eternity has nearly passed. Around a neutron star, the very concept of direction is distorted. Upward and outward, which should represent freedom, become steep climbs along a warped surface of space-time. The photon begins its journey full of determination, racing at the ultimate speed. Yet each moment it travels outward, time itself stretches and space stretches beneath it. From our viewpoint, the photon appears to weaken, as if running up an impossibly long incline, but it is not slowing. It is merely struggling against the deep valley carved by gravity. This extraordinary environment has consequences that go far beyond simple bending of light. The star's intense gravity squeezes matter so tightly that atoms lose their identity. Neutrons pack together until the star resembles a single gigantic atomic nucleus. This density amplifies gravitation to a level where escape becomes a negotiation between motion and geometry. A photon emerging from this region is like a climber ascending a mountain that reshapes itself while being climbed. The landscape shifts with every step. Some neutron stars have surfaces so curved that photons are pushed sideways as they attempt to leave. Instead of flying straight outward, they arc around the star in long sweeping paths that may wrap partially around the sphere. Imagine tossing a ball into the air and watching it curve behind you instead of falling to the ground. The light that leaves a neutron star surface does not simply go up. It explores pathways that look impossible in ordinary space. This leads to one of the most astonishing visual consequences of neutron star curvature. If your eyes could survive the intensity of radiation and you could somehow stand on that surface, you would see almost the entire sphere around you. The region behind the star would not be hidden. Light from that hidden side would curve over the top and arrive before your eyes. The star would reveal itself completely, a view found nowhere else in the universe. The surface would look like a world wrapped inside out by its own gravity. As light fights its way away from the star, the time it takes becomes unpredictable. A photon that leaves from one location may take far longer to escape than a photon from another nearby point. The difference might depend only on a microscopic shift in angle. If directed too low, the photon will hug the star's surface and loop before rising. If angled slightly higher, it may fly out with only a minor delay. The boundary between an easy escape and a nearly impossible one is frighteningly thin. These complexities shape what astronomers observe. When we measure the pulses from a spinning neutron star, the timing is influenced not only by the rotation, but also by how long the photons spent struggling upward. The star spins, magnetic fields flare, radiation bursts outward, but the arrival of that radiation is slowed and distorted by gravity. The light from the same event can arrive scattered in time, as if the star were echoing its own heartbeat. Even more dramatic conditions occur when neutron stars collide. Two of these dense objects spiraling toward each other create gravitational tides so intense that photons born in the final moments before merger might circle repeatedly, caught between the two monstrous gravity wells. Some photons may escape only after the stars have already merged into something new and darker. Their message arrives late, telling us a story that no longer exists. We also observe neutron stars feeding on companion stars. Gas torn from the companion falls onto the neutron star surface. As the gas strikes the surface, it releases bursts of light and heat. But gravity reshapes these bursts. Some photons are pushed outward directly. Others become tangled in looping paths just above the surface, bouncing around until they finally find an exit. These delays turn a single violent event into a drawn-out flicker when seen from afar. The universe around a neutron star is filled with curved roads that turn any journey into a labyrinth. Light can wander for ages mere meters above the star surface. It can orbit once or twice before it discovers an exit. And while it wanders, time for the photon remains non-existent. It does not feel the weight. But we, watching across space, observe the hesitation like a story retold slowly. This distortion of escape makes neutron stars almost behave like black holes, though they fall short of the final transformation. They do not possess an event horizon. They have not crossed the line where outward ceases to exist. But they show us that nature does not switch between freedom and total imprisonment abruptly. There is a tremendous gray area where light is not free, yet not lost, where its future remains uncertain. As the neutron star ages, its rotation may slow, but its gravity remains relentless. Photons emitted from its surface forever face the struggle. The star never relaxes its hold. Even after billions of years, a neutron star remains a monument to uncompromising curvature. It reminds us that even when speed is absolute, direction determines destiny. Light can remain trapped in the narrowest of cages if the walls are made of bent space rather than metal. Neutron stars prove that trapping light is not reserved only for black holes. They demonstrate the spectrum of captivity. A photon may have every possibility of escape, yet still spend eons confined near a surface only a few kilometers across. This is captivity measured not by prohibition, but by duration. And so we realize, even without the final collapse, gravity can push light toward imprisonment. The difference between a neutron star and a black hole is not one of essence, but of completeness. The star has almost succeeded in constructing a perfect trap. It has nearly erased all future outward. But nearly is not enough for true darkness. A neutron star stands at the brink of a profound transformation. It is already so dense that space around it bends like a wave cresting before it breaks. Yet the star has not surrendered its identity. It has not crossed the invisible threshold that would turn its surface into a boundary of no return. It still shines. It still speaks through photons that manage to escape its gravity well. And because those photons struggle so clearly and so visibly, neutron stars reveal the fragile balance between freedom and confinement better than any other object in the cosmos. Every photon that leaves a neutron star carries scars of the attempt. Its wavelength has stretched because the climb has drained energy. The color that begins bright may shift into deep crimson. If the climb is long enough, the photon may slip beyond human detection entirely, becoming part of invisible radiance known only to instruments capable of sensing faint whispers of energy. The message is still there, but it has been altered by hardship. Even time shows its strain near a neutron star. A clock placed on the surface would tick slower than one far away. The difference is not small, it is dramatic. Time itself is imprisoned by curvature. The heartbeats of the neutron star slow when viewed from a peaceful corner of the universe. Minutes near the surface might match hours or longer beyond the star. Light does not slow, yet moments themselves become stretched like soft clay under the weight of gravity. This distortion leads to a striking concept. If a neutron star could exist forever without collapsing further, some photons emitted early in its history might still be crawling outward today. They are in motion, yet appear frozen. They are not lost, yet they have not arrived. This is what near imprisonment looks like. The photon has not been trapped absolutely, but from the perspective of distant observers, it may as well be held captive for eternity. The same struggle plays out in the hearts of galaxies, where neutron stars populate the cosmic wilderness. When a neutron star rotates, its magnetic field can whip space into spirals of energy. Photons caught in the twisting magnetic regions may be spun around the star, like dancers tied to a turning wheel. These photons eventually escape, but only after surrendering to motion dictated by the geometry. Their story becomes longer and more complex. By the time they reach our telescopes, they have lived through battles with gravity that we can only imagine. Neutron stars can also bend the paths of light from background stars. When one passes in front of a distant source, gravity magnifies and shifts the incoming photons. The distant star may appear brighter or doubled, or it may flicker in surprising ways. These moments prove that even a small object by cosmic standards can warp the universe enough to twist light into unexpected shapes. It does not take a supermassive giant to sculpt geometry into a cage. A star the size of a city can nearly trap light if packed densely enough. And yet, there remains one crucial difference. The neutron star does not close every door. Light that tries hard enough or lucks into a clear trajectory eventually finds the path outward. The photon may be delayed, it may be diminished, it may be exhausted in every way except speed. But it survives. It returns to open space where geometry relaxes and the universe becomes wide again. This makes neutron stars invaluable to understanding the boundary of extreme gravity. They show where the line is drawn and how that line can shift. They are a living demonstration of gravity, almost solving the riddle of confinement, but falling short by a breath. A neutron star is a warning sign that nature can come close to the perfect trap without achieving it. That light can lose nearly all its freedom, but not every last possibility. There is melancholy in that state. The photon moves without rest, but cannot decide its future. It is like a messenger stranded in a labyrinth, knowing the exit exists somewhere, but unable to locate the one correct passage. The universe grants speed without choice. The result is motion that may persist longer than stars themselves. If light could speak, what would it tell us about such a place? Perhaps it would describe corridors of space that twist unexpectedly. Perhaps it would recall how time lengthened beneath its path. Perhaps it would say that escape is a matter of patience beyond comprehension. But photons do not speak. They only arrive when they can and allow us to interpret their silence. A neutron star stands firm against collapse for as long as its structure allows, but gravity never stops pressing inward. If the star acquires enough additional mass, or if internal changes remove its remaining defenses, then the curvature will finally tip beyond the critical point. The pathways outward will collapse into inward spirals. Light will attempt to leave, and discover that outward has ceased to be a direction at all. The star will fall into permanent night. A horizon will form. The photon sphere will appear. And a black hole will be born, where once there was a struggling survivor. For now, neutron stars are guardians of the edge, showing us the last stage before the event horizon claims dominance. They are reminders that escape is never guaranteed by velocity alone. They are stepping stones that lead straight to the question at the heart of this journey. If neutron stars can steal so much freedom from light without truly imprisoning it, then what of stars that have not yet collapsed? How far can gravity push curvature before the star loses control? Is there a point where light hesitates even around a living star, not yet crushed into a neutron star destiny? To explore that possibility, we must step back to stars on the brink of collapse. Stars massive enough to teeter between brilliance and ruin. Stars where light is not yet trapped, but certainly delayed. The universe does not leap suddenly into the impossible. It approaches thresholds slowly, offering previews along the way. There are stars in the universe so massive that they live their entire lives in defiance of gravity. These giants shine with a fury that pushes outward against the darkness. Their radiation is not gentle. It is a relentless pressure born from nuclear fire deep within their cores. This outward pressure keeps gravity from winning too soon. Without it, the star would collapse under its own weight in a heartbeat. But even the brightest furnace cannot burn forever. When the fuel thins and the pressure fades, gravity begins to reclaim what was borrowed. A very massive star lives on the edge of catastrophe from the moment it is born. Its intense gravity bends space-time strongly, even while the star still burns. Light that attempts to leave its surface must climb a steep gravitational well. The photons do escape, but they do so with effort. The star glow is a message that travels through curved geometry, weaker and slower to appear than the raw energy behind it. If the star were only a little denser, or its radius only a little smaller, then the light would begin to slow in its escape so dramatically that observers far away would see the star dim before their eyes. Such stars stretch the definition of freedom. A photon at their surface still moves at the ultimate speed within its own local frame. But the road upward has grown long and twisted. Some photons follow paths that barely clear the star edges, curving almost into orbits before spiraling outward again. They linger near the surface like hesitant travelers, unsure whether the sky is truly open. Others loop once or twice before reaching space, delaying their journey by seconds or years depending on the star mass and size. Geometry becomes a maze that photons solve imperfectly. The star interior is a battle zone. Gravity demands collapse. The core resists by creating heat and light through fusion. But as heavier elements accumulate, fusion can no longer release enough energy to maintain the outward push. The star begins to contract. The gravitational well deepens. Light takes longer to escape. Radiation that once streamed freely now hesitates. The star appears to darken, even though its core grows hotter. It is a warning that collapse has begun. There is a moment in this downward spiral when the star becomes so compact that light on the surface is barely able to claim victory over gravity. If the star shrinks to 1.5 times the radius that would form a black hole, it reaches the same critical geometry where photons could orbit in precarious loops. Yet in a living star, radiation pressure within the core prevents full surrender. The photon sphere does not form as neatly as it does around a black hole. Instead, there exists a chaotic region where photons may whirl and stall before their final escape. During this phase, the star can resemble a star wrapped in its own trapped light. Photons leaving the core bombard the outer layers from within, trying to push downward as much as outward. The pressure is immense. The star swells and trembles. Some massive stars enter an unstable state where they shed outer layers in gargantuan eruptions. These convulsions briefly lighten the star mass, but they also mark the growing power of gravity still lurking beneath. The outward glow becomes a desperate attempt to remain visible. If the star happens to be in a dense environment where gas and dust surround it, the light that manages to escape will scatter across the region, creating brilliant nebulas that shimmer like cosmic warnings. Yet even these displays are signs that the internal struggle continues. Gravity is not yet victorious, but its triumph feels inevitable. Very massive stars show us that trapping light is not a privilege reserved for dead objects like black holes. Even stars that are alive, burning, and luminous can nearly imprison their own radiance. Not through absolute confinement, but through long and exhausting delay. Photons must navigate rising curvature that steals energy and bends pathways inward. The star becomes a near prison. Time within its influence moves slower than time outside. The dance toward collapse is played out not only through motion of matter, but through the desperate journeys of light. If the star finally exhausts all fuel, the battle ends suddenly. The core collapses and the outer layers fall inward. In a fraction of a second, gravity overwhelms every remaining force. Space-time caves inward sharply. If the collapse continues without limit, a black hole emerges. The surface where photons once struggled becomes an event horizon. The star does not fade. It disappears behind a boundary where outward ceases to exist. Yet not every very massive star becomes a black hole instantly. Some explode outward with such force that the core survives in a more modest state as a neutron star. Others collapse partially and then flare explosively, only to collapse further. There are complex fates determined by mass, rotation, magnetic fields, and the unpredictable chaos of stellar death. But each path leads through a period where light is on the edge of being trapped, held for agonizing spans that stretch the meaning of time. Very massive stars teach us that confinement of light is built into the journey toward collapse. It begins before the star meets the definition of a black hole. It begins when gravity first gains more strength than radiation can provide. The star does not need a perfect horizon to cage photons. It only needs to bend the road ahead so tightly that the escape route weakens with every heartbeat of the star. It is astonishing to realize that long before a black hole forms, a star can create a region where freedom is nearly lost. Light escapes only because the star has not yet become dense enough. The difference between nearly trapped and fully trapped lies in that shrinking radius. As the star shrinks, time slows. Photons take longer to depart. Observers far away see the star flicker and fade. We are witnessing a countdown measured in distorted moments. If the star collapses just a little more, the geometry will pass the edge of possibility. The photon sphere will form. The event horizon will follow. The star story will end as all light becomes part of a silent region that no longer communicates with the universe. Very massive stars stand as the final testimony that true confinement does not require a sudden change. It unfolds gradually through deepening curvature and lengthening delays. Light begins as master of motion, but becomes a reluctant explorer of twisted space. The star is still alive, but its future is written in the way light struggles to leave. Soon, gravity will take the last remaining option away. The star will no longer allow photons to choose outward. And when outward disappears, light will discover that speed is powerless without direction. There are ideas in theoretical physics that imagine the universe containing objects beyond the familiar. Stars made not of atoms, but of exotic forms of matter that bend space-time in new and powerful ways. These hypothetical structures challenge our understanding of what gravity can do. Among the most intriguing possibilities are objects that could trap light without ever forming a black hole. They would become gravitational cages where photons circle endlessly, neither escaping nor falling into darkness. One idea is the boson star. Unlike the stars we know, which are built from protons and neutrons, a boson star would consist of particles that obey different quantum rules. Bosons can overlap in space. They can gather densely without pushing each other apart like ordinary matter does. If enough bosons collected under gravity, they might form an object far more compact than any normal star. The curvature near its surface could grow deep enough for light to orbit in stable loops. Unlike the unstable orbits at a black hole photon sphere, these photon paths might remain balanced forever. The star would glow only if light or radiation became trapped inside and circled perpetually, unable to escape, but also unable to fall in. Another imagined structure is the Grava star. It would form when a collapsing star is stopped just before becoming a black hole. Its interior space-time would take on a strange character, supported by exotic energy that resists further collapse. The surface would be thin and incredibly dense. Light approaching that boundary could become trapped in repeating paths that skim constantly along the surface, like a bird circling endlessly around walls it cannot see through. A Grava star might look almost identical to a black hole from far away, but it would lack an event horizon. Light would be delayed for unreal spans of time, but ultimately still free in principle. Dark matter stars add yet another possibility. Dark matter does not interact strongly with ordinary matter or light, yet its gravity influences galaxies and holds them together. If enough dark matter concentrated into a small enough region, it might form a star-like shape without the heat and pressure generated by fusion. Such an object could be extremely compact. Its gravitational pull could nearly confine photons, letting them orbit close to the core. The orbits might be stable or unstable depending on the dark matter nature, but either way, the photons would spend long ages circling a darkness that does not shine. Each of these structures asks a daring question. Can space-time be shaped into a prison without sealing it completely? Can light be confined not by a boundary that forbids escape, but by a geometry that makes escape nearly impossible? These hypothetical megastructures suggest that the answer could be yes. Gravity might create traps without horizons. If such objects exist, they would alter our interpretation of the cosmos. A distant gravitational cage could mimic a black hole in many ways. Matter falling toward it would accelerate and heat, emitting bursts of radiation. That radiation might then skim the structure in tight loops before escaping, creating a glow like the halo around a black hole shadow. To our telescopes, the cage could look like a black hole with a slightly brighter core. The difference would emerge only after long study of how light behaves near the edge. Stable photon orbits are the key distinction. Black holes allow photons to orbit only at one precise distance, and even there the orbit is unstable. A tiny disturbance guarantees a fall inward or a rise outward. But these hypothetical objects could support stable rings of light that persist. This possibility fascinates physicists, because such stable orbits would represent a form of trapped light that does not require sealing the universe from within. Geometry alone could hold photons captive forever. The cosmos may contain experiments already performed by nature. Some gravitational lenses we observe appear more complex than what ordinary stars or black holes would produce. Strangely, bright rings and repeated patterns of light might hint at exotic mass distributions that bend space with unfamiliar precision. We do not yet understand every lens we see. Some may be illusions caused by galaxies within galaxies, but some may be hints of structures that challenge the rules we have grown used to. Even time behaves oddly in these imagined environments. The gravitational cage slows time near its surface drastically. A photon circling close to the core might complete countless revolutions in what feels like a single instant locally, while observers in calmer space watch those same revolutions stretch into ages. The photon remains stuck both in path and in temporal distortion. Motion does not mean progress. Speed does not guarantee change. These objects are theoretical, but they are not fantasy. The equations of general relativity allow such forms of matter and geometry. Quantum field theories propose bosons that could cluster into dense cores. Dark matter, though mysterious, is known to fill the universe. Gravastars exist in the mathematics of collapse models. What we do not yet know is whether the universe chooses to build these forms, or whether they remain ideas waiting for creation. If gravitational cages exist, they are not perfect prisons. Light caught inside is not doomed to fall inward forever. It remains in motion, sustained by the same rule that keeps photons unstoppable. But the destination is denied. The photon experiences a journey without escape, a loop without an exit, a story without resolution. These megastructures show us that gravity can trap light from the outside inward instead of from the inside outward. They redesign the meaning of confinement. The trap does not need a final barrier. It can simply eliminate the path that leads away from the center. Understanding these possibilities widens our definition of what control gravity can have. It can silence light through collapse or confuse it through curvature. It can delay or detain without ever needing to forbid. The idea of gravitational cages reveals that imprisonment is a spectrum, and at every point along that spectrum, light remains obedient. We do not yet know whether these exotic objects truly shine or hide somewhere in the cosmic wilderness. But if they exist, they remind us of one truth that grows stronger with each chapter of this journey. Gravity does not need to hold light still in order to trap it. It only needs to give light a path that always leads back to where it began. When people imagine a trap for light, they think of something small, a star, a black hole, a region where gravity becomes sharp and deadly. But Einstein taught us to consider a far grander possibility. What if the entire universe were curved in such a way that light could never escape? Not because of any single object, but because space itself loops around on the largest scale imaginable. In a universe that is spatially closed, a photon launched into the cosmos might travel forever without ever reaching an edge, because there is no edge to reach. The photon would eventually return to the point where it began, completing a journey across the shape of existence. A closed universe is a place without boundaries. It does not expand outward into emptiness. Instead, it curves back upon itself, like the surface of a planet does in 2 dimensions. A traveler who walks straight across Earth forever eventually returns to the starting point. There was no wall blocking the path. There was only curvature. Now imagine that idea stretched into 3 dimensions, into the very fabric of the cosmos. Light sent in any direction would trace a path that ultimately returns home. In such a world, every photon is both free and trapped. It races through space at full speed, yet space has no direction that leads to escape. The universe itself becomes the cage. There is no horizon, no singular object causing the confinement. Instead, the geometry of the entire cosmos dictates that leaving forever is impossible. The photon is never slowed or turned around. It simply continues onward until onward carries it in a full circle. Einstein once considered that our universe might be exactly such a place. He imagined the cosmos as finite in size but without edges, a realm where the total mass curves space-time inward so gently that we do not notice the eventual wraparound. The idea was simple. The universe contains matter. Matter curves space. If there is enough matter, the curvature will be strong enough to fold space back upon itself entirely. In a fully closed universe, light would create echoes of creation itself. A flash of radiation, once emitted, would travel around and around, returning again and again after crossing cosmic distances that take billions of years. The universe would be filled with repeating signals. Ancient events would never fully fade. The birth of stars might be witnessed again far into the future as photons complete new circuits around the cosmos. The night sky would become a tapestry woven from recurring memories. For a moment in history, this model seemed possible. But new discoveries changed the picture. Astronomers found that the universe is not static. It is expanding. Galaxies rush away from one another. Space itself stretches. The farther a beam of light travels, the more that stretching slows its progress. The wavelengths lengthen. Energy drains. The photon grows more and more red as its message tires. Today, the expansion of the cosmos accelerates due to a mysterious form of energy we call dark energy. Instead of curving inward into a loop, space appears to be stretching outward faster and faster. Distances grow too quickly for photons ever to complete a full circuit. The universe seems too open for closure. Light is not trapped globally because the cosmic landscape is expanding beneath it. Every moment adds more distance between points. The finish line retreats faster than the photon can circle around. But this does not erase the idea. It only delays the question. If the expansion were to slow in the distant future, or reverse into contraction, or take on forms we do not yet understand, the universe might still curve into a cosmic loop. At that point, light could once again become a prisoner of the universe itself. This possibility is not ruled out by the laws of physics. It simply awaits answers we do not yet possess. Even now, hints of large-scale curvature linger in debate. Measurements of cosmic geometry must reach extraordinary precision before we can be certain of the universe shape. Some findings suggest slight curvature, not enough to close the cosmos fully, but enough to remind us that the question remains open. Whether this is a true signal or merely illusion created by complex measurements is still unknown. A closed universe would redefine imprisonment. Light would run forever, yet never escape. The trap would not be a dark object or a collapse of order. It would be the entire fabric of existence bending into a circle. There would be no outside, no beyond, no place for photons to flee. Their speed would remain perfect. Their energy might diminish slowly, but their motion would never cease. They would be free travelers on an endless road that only looks infinite because it always returns to where it began. This idea is humbling. It suggests that boundaries may be illusions. What appears to be infinite might simply be a journey so vast that its completion lies far beyond comprehension. It also suggests that freedom itself is defined by geometry at every scale. Light cannot outrun the shape of the universe. It can only reveal it. Each photon is a surveyor drawing the map of space-time by its motion. In a closed cosmos, that map would reveal itself as a loop. For now, the universe does not appear to be trapping light in this universal way. The cosmic expansion keeps escape alive. Photons continue their travels outward into growing space. The horizon of the visible universe grows not because light reaches farther, but because space stretches more. Freedom at the largest scale seems preserved, and yet the idea remains. It waits in the realm of what if and what might be. If expansion slows, if geometry evolves, if the universe chooses closure instead of drift, then every photon will discover that no matter how fast it runs, it is destined to revisit its origin. The cosmic trap is not a threat. It is a possibility that reminds us that gravity rules not only the tiniest orbits near the edge of collapse, but also the pathways that span across everything that exists. In such a universe, light would still be relentless. It would still be unstoppable, but it would run in circles drawn by the hands of creation itself. Freedom and confinement would become the same thing. Motion would continue always, but escape would be an illusion, forever out of reach. Gravity does not only bend the routes that photons travel, it bends the rhythm of existence itself. Time, which we often think of as a constant drumbeat, shifts and distorts under the influence of mass. Clocks deeper inside a gravitational well tick slower than clocks far away. This effect is not imagination, it is real and measurable. Place two identical clocks at different heights on Earth, and the lower one will lag behind. The difference is tiny here, but around denser objects the slowdown becomes dramatic. Time itself becomes a form of confinement. Imagine a photon near the surface of a collapsing star. Locally, it moves at the ultimate speed. It sees no difference in the flow of reality. Yet to a distant observer, that same photon appears stuck, barely making progress. Seconds near the star correspond to minutes or hours far from it. If the collapse continues, the discrepancy grows and grows until one moment near the surface stretches into eternity beyond it. The photon has not slowed, but time around it has nearly stopped. This is how light can be imprisoned without ever being caught. If time in a region becomes slow enough, then from the perspective of the universe outside, the photon never leaves. It could take longer than the age of galaxies to cross a distance as small as a mountain. The world around it continues to evolve. Stars are born and die. Civilizations rise and fall. But the photon remains in the same moment because that moment refuses to move forward. In the final stages before a star becomes a black hole, this effect grows so powerful that the light emitted near the forming horizon appears to freeze. The photon descends into a trench of warped time. Though it races onward in its own frame, we see it drift slower and slower, fading gradually into deeper red until it vanishes from sight. Far away, we watch the last light from the collapsing star hover, trapped by the weight of time rather than by any barrier of space. We call this effect gravitational time dilation. It transforms time into a slope, steeper as mass compresses. A photon, beginning its escape near a very massive object, must climb upward, not only through twisted space, but through slowed time. Each step upward requires it to borrow energy from its own wavelength, stretching it longer and longer. If the time slope grows infinitely steep, the photon can never climb high enough to escape the moment in which it was born. It remains eternally suspended on the edge of freedom. There is something haunting in the idea that light can be caught by time alone. A photon trapped in this way does not orbit endlessly or bounce between curved paths. It does not fall. It does not rise. It simply endures, unable to share its story with the outside universe. This kind of capture is quiet. No motion reveals the imprisonment. Only the absence of change betrays the trap. Even without forming a black hole, some objects compress matter so fiercely that their surrounding time becomes noticeably slower. Neutron stars show this vividly. A clock on their surface would lag far behind one floating freely in interstellar space. Photons leaving that surface carry the mark of delayed time. Their journey upward is stretched. The signals they carry arrive late. They do not orbit as they might near a photon sphere, but delay becomes its own barrier. Light is not forbidden to escape. It is simply told to wait longer than should be possible. Time dilation also plays a role on cosmic scales. As the universe expands, the flow of time can differ between distant regions. Light that travels through deep gravitational valleys created by galaxy clusters arrives later and redder than expected. On the largest scales, time becomes a landscape with hills and valleys, as real as any mountain range. Photons cross that landscape, and each contour shifts their place within the cosmic story. These distortions remind us that time is not a neutral witness. It is an active participant in the drama of motion. When gravity grows strong enough, time becomes a prison cell without walls. Photons inside that cell never stop moving. But movement loses meaning when the future barely advances. This challenges our intuition. We imagine freedom as the ability to move from place to place. But what does freedom mean if you can never move into the next moment? A photon caught by extreme gravity exists forever in a shrinking sliver of time. For that photon, every attempt to leave the region becomes an illusion. It does not arrive anywhere new, because the future it tries to reach has grown impossibly distant. So far, we have seen how space can trap light by twisting its pathways into circles. Now we see how time can trap light by slowing the flow of change until the world outside moves forward alone. These prisons work together. A photon can be trapped spatially by curvature or temporally by dilation. When both occur at once, the cage becomes nearly complete. Time is the most subtle jailer of light. It does not resist motion. It does not bend the straight path. It does not reduce speed. It simply removes the future from reach. Under the influence of gravity, time becomes elastic, stretched thin in some regions, compressed in others. And where time stretches too far, light becomes stuck without ever stopping. This means that even before a black hole forms, the universe can build environments where photons remain for ages immeasurable. They will eventually find freedom, but the wait grows so long that escape becomes indistinguishable from eternal confinement. The difference lies only in which frame of reference you choose to believe. This realization leaves us with a deeper question. If light can be delayed into illusion, redirected into loops, or held in moments that barely tick forward, then what exactly does it mean to trap light? At what point do we say that freedom has been lost? Is a photon that escapes after 1 trillion years truly free? Or has the universe already decided its imprisonment long before we see the final result? As we approach these final questions, we come closer to the heart of what gravity does. It does not fight motion. It shapes possibility. It turns time and space into boundaries that light cannot ignore. Even the most relentless traveler in creation must obey the architecture it races through. Light is the ultimate traveler. It does not hesitate. It does not wander uncertainly. It surges forward at the fastest speed the universe allows, crossing worlds and galaxies, revealing everything that shines, and even some things that do not. We build our understanding of the cosmos upon the faithfulness of photons. They bring us the truth of distant stars and ancient events. They are historians carved from pure energy. But what happens when gravity interferes so deeply that the photon journey is delayed beyond recognition? When it loops around a star for ages? When it spends eternities trying to climb out of a steep valley of space-time? When time itself stretches around it until the future seems unreachable? At which point do we stop calling this motion freedom and start calling it captivity? The first step to answering this question is to be precise about what trapping means. Light cannot slow below its ultimate speed. It cannot stop in space. A photon at rest is a contradiction that nature refuses to create. This makes trapping fundamentally different from imprisoning matter. A rock dropped into a deep pit can remain motionless and unseen, but a photon continues onward regardless of circumstance. To trap light is not to hold it still. It is to remove every possible future direction that leads away from the prison. The photon becomes a runner whose path loops endlessly, a messenger whose message never arrives. Gravity accomplishes this not through contact or force in the traditional sense. The photon has no mass for gravity to pull. Instead, gravity transforms the very geometry through which motion occurs. It shapes the geodesics that define the straightest possible lines. If those lines curve inward or fold back, the photon must obey. Its speed cannot help it when the road beneath its feet leads in circles. We have seen throughout this book that trapping light is a matter of bending each of the two pillars the photon relies on to define progress. One pillar is space. A photon travels through space. Remove the outward direction and its path becomes confined. The other pillar is time. A photon relies on the forward march of moments to reach new places. If time freezes or stretches without end, escape becomes meaningless. Motion refuses to update the future. Spatial trapping is the most familiar version. The classic example is the photon sphere of a black hole. At the precise distance where outward curvature equals inward curvature, a photon can circle the black hole endlessly. But that orbit is unstable. The smallest nudge ends the balance. Either the photon escapes outward or falls inward into the lightless well where time and space switch roles. Yet even an unstable prison is still a prison, when it holds light long enough for the outside universe to forget it exists. Neutron stars and ultra-compact stars bring us close to similar traps without crossing the critical line. Their geometry almost allows a photon sphere to form, but not fully. Light hugs their surfaces, unsure of its path. It may spiral for ages before achieving escape. The photon remains locally free but globally delayed, and delay can grow so great that escape becomes indistinguishable from loss. Meanwhile, hypothetical megastructures like boson stars and gravastars tease us with the possibility of true confinement without horizons. They might one day be discovered, or they might remain beautiful fictions, but their mathematical foundation reveals a sharp truth. Light can be trapped by rules far more subtle than a collapsing star. Geometry alone is enough if shaped precisely. The photon does not need a wall to prevent escape. It only needs a world without exits. Time trapping is subtler, but equally powerful. In the slowing of clocks near massive objects, light reveals a new kind of confinement. A photon can keep moving, but never arrive. The events that mark its progress may tick forward so slowly that distant observers see it remain in one place indefinitely. Light becomes part of a moment stretched thin, unwilling to move toward a future it can still reach, but cannot reach soon enough. This is where definitions break down. A photon on the verge of falling into a newborn black hole seems trapped to us long before it crosses any horizon. It appears to hover in place. It appears to surrender. It appears gone. But the photon is still moving. It is still attempting to escape. The horizon simply forms beneath its feet, faster than it can climb. The universe eats the future from behind it. So what does trapping mean when motion never ceases? It means that motion has lost meaning. It means that progress has become a closed set, either circular in space or frozen in time. It means light continues to journey eternally, yet fails to find a destination that lies beyond its prison. A photon that orbits a black hole forever has become trapped by spatial confinement. A photon slowed by time dilation until its arrival is postponed beyond the lifespan of the universe is trapped by temporal confinement. A photon caught in a closed universe may run endlessly, yet always return to its starting point. It is trapped by the cosmic scale of geometry itself. We realize that trapping is not a binary property. It exists on a spectrum. Some photons are nearly free. Some are nearly imprisoned. Some escape after a delay. Some remain lost for as long as space endures. The difference is determined by how completely the universe removes the paths that lead outward. There is a poetic consequence to this view. Freedom is not defined by speed. The photon has the greatest speed possible, yet its freedom is fragile. Freedom is defined by options. by direction. Speed without direction is a sprint within a cell. A photon rushing around the photon sphere is doomed to be the fastest prisoner imaginable, racing forever along a road that returns to its beginning. Physics gives us the equations to predict these motions. Einstein gives us the metrics that define the shapes of space and time. But those equations cannot answer a philosophical question disguised inside a scientific one. When does almost trapped become trapped? When does a delay so long become confinement? When does an orbit so perfect become a cage? Perhaps the answer depends on perspective. To an observer falling into a black hole, the photon that circles near the horizon is free. It appears to shoot past with ease. To the observer far away, the same photon hangs frozen on the edge of oblivion. Perspective creates its own truth. Yet the most universal truth remains this: a photon that cannot reach new observers has lost its role as messenger. It may still exist, it may still move, but it can no longer be seen. Its information is removed from the cosmos. That is the strictest definition of light trapped. And that strict definition leads us always to a single answer. There is only one environment known where light truly loses all possible futures. Only one form of curvature that erases every outward direction. Only one structure in which a photon can neither escape nor linger forever at the edge. Only in the final collapse does geometry stop giving options at all. Trapping light is not a matter of slowing or catching. It is a matter of eliminating every possible path that leads somewhere else. Gravity can come close in many ways. It can weaken those paths. It can fold them inward. It can create delays beyond understanding. But true confinement demands that the path disappears entirely. If there remains even one thread of geometry that leads outward, no matter how faint, the photon remains technically free. It may wait through ages. It may circle through endless loops. It may see time freeze for those who watch. But eventually, if the thread exists, light can find it. There is only one way the universe cuts that thread. Every journey of light through the universe follows the shape of space-time. Every twist in that path reveals a new aspect of gravity power. We have seen stars that nearly trap light, neutron stars that hold photons in hesitation, and hypothetical objects that might cage them in endless loops. All of these come close to a remarkable threshold. They sculpt space-time so intensely that escape becomes nearly impossible. Yet each falls short in one crucial way. They leave at least one direction outward. A single route, narrow and fragile though it may be, still exists. And where one path remains, freedom still survives. The boundary between almost trapped and trapped forever is sharp. It is set by a simple relationship between mass and radius. Compress enough mass into a small enough region, and the geometry changes in a way no force can resist. Outward ceases to be a direction at all. The point at which this occurs is defined by the Schwarzschild condition. If an object radius shrinks to less than the value determined by 2 times its mass, multiplied by Newton constant, and divided by the speed of light squared, space-time curves inward completely. Light cannot climb out. Gravity removes all possibilities. This radius marks the event horizon. Cross it, and even photons cannot tell their story again. Before an object reaches that final density, even if it approaches extremely close, photons still retain a future outside its grasp. Gravity may delay their escape by ages. It may force them to loop repeatedly. It may stretch time so mercilessly that each instant becomes centuries to distant observers. But the path outward exists. And that single truth means the object is still visible. It is not yet a black hole. This threshold is surprisingly specific. An object must become compact enough that its radius is less than 1.5 times the Schwarzschild boundary to hold light in orbit. That forms the photon sphere. Yet even then the orbits remain unstable. One breath of disturbance alters the destiny of the photon. Outward or inward are still available. The photon is almost lost, but not completely. The object occupies a liminal place, a twilight between visibility and disappearance. As collapse continues, the geometry deepens. Space-time bends so strongly inward that light from the surface becomes more and more redshifted. This redshift is not a trick of distance. It is the cost that photons pay to climb through a warping of time. Their energy drains away. Their message grows faint. To the universe beyond, the object seems to dim, even if its core burns hotter than ever. The struggle to escape defines the perception of brightness. When the radius shrinks to precisely 1.5 times the Schwarzschild value, the curvature becomes extreme enough that a photon placed at that distance can circle infinitely. Yet because the orbit is delicate, a photon rarely remains there long. Even the slightest influence pushes it away. One push inward ends the story. One push outward grants a long but possible escape. The photon sphere is the brink, the last position where light remains undecided. Everything deeper than that brink brings the photon into a new geometry. Outward begins to fade. The idea of distance away from the center loses meaning. The slope of time becomes overwhelmingly steep. Photons shot upward no longer appear to rise. They stall. Their wavelengths stretch indefinitely. Observers far away see them freeze at the edge of night, dimming and fading, but never crossing the line. This is the illusion of falling into a black hole. The photon never seems to pass the horizon, but this illusion belongs only to the observer outside. In the photon's own reality, the fall continues without hesitation. Eventually, no disturbance can save the photon. The final curvature forms the event horizon. Beyond this surface, outward vanishes. No geodesic leads to a place where signals can escape. The photon remains fast, but without any path that reaches beyond the horizon. No amount of energy, no frantic search for direction can undo the geometry. It has become trapped absolutely. The information it carried is removed from the visible universe. The photon may still exist and move and follow space-time, but its story will now be told only inside the darkness. Everything that came before was almost a trap. Only this is a completed one. This makes black holes extraordinary, not because they are dangerous, but because they are perfect. They demand absolute obedience from motion. They demonstrate that freedom depends entirely on geometry. The boundary they create is not a structure or a barrier. It is the end of possibility. Outside the event horizon, decisions are still possible. Inside, there are none. Even time flows inward. When we ask whether light can be trapped without a black hole, the universe offers many examples where the answer feels like yes. Stars, neutron stars, exotic objects, and even the entire cosmos under certain curvatures can hold light for eons. But if the question demands certainty, if the definition requires that no path outward exists, then there is only one answer. Only black holes trap light completely. This is not a failure of other objects. It is a reminder that trapping is a condition defined by the geometry of possibility. A star that delays photons for 1 trillion years is still not a black hole. A neutron star that bends paths into tight spirals still leaves an escape route. A closed universe that loops photons endlessly still allows the photon to see the outside world it has looped around. Only the event horizon removes outward from the vocabulary of space. The difference between almost and absolute remains a single boundary drawn by gravity itself, and that boundary separates the visible from the silent. Nearly trapped light still fulfills its purpose. It still brings information to distant worlds and distant times. Trapped light falls into a quiet the universe cannot break. It becomes part of a secret interior that will never again communicate with cosmic history. We end this journey where the universe ends its stories, at the place where photons lose their future and space loses its escape, at the place where speed bows to geometry. Light is relentless. It is unstoppable. It is the fastest traveler in existence. But even the unstoppable can be directed into a coffin of curved reality. At the event horizon, movement continues forever, but progress dies. Gravity can bend light. Gravity can bind light. Only a black hole can bury light forever.